Thanks very much. So because I am standing in between you and lunch, I'm going to bring you my take-home message, which is that the ionization of the circumgalactic medium is significantly different at a redshift of 5.5 compared with a redshift of 6. So the logical cause for this is a weaker or softer UVB due to reionization at a redshift of 6. And we're taking this as evidence of a late reionization continuing to occur in metal-enriched and therefore biased regions of the universe. So over this short period of cosmic time, the evidence that we have is that carbon-4 declines, carbon-2 increases. There's an increase in the amount of oxygen-1 that we see in the circumgalactic medium, and that's particularly significant because oxygen-1 is in close charge exchange with the hydrogen. And we also see a flat evolution in weak magnesium-2, despite what you would expect over this cosmic time, there to be a decline in the amount of metals. Okay, that's my expert summary. I understand that we have a broad audience, so now I'm going to step back and give you the bigger picture. Okay, so setting the scene in the intergalactic medium. So hydrogen reionization is ongoing at a redshift less than 6. And this took a little bit of time for that to gain traction within the community because there were earlier C&B results that told us that reionization probably occurred at a larger redshift, and then that came down. And the real test for this came in the Gunn-Peterson troughs that were found, and these massive Gunn-Peterson troughs. So this one here is 110 co-moving megaparsecs in length. And you can see it here. Is that coming up? Yep, okay. Here in the spectra towards this high redshift quasar. And it's also reproduced in large-scale cosmological simulations, and the technique that we use is having a quasar out at some higher redshift, and we look along the line of sight and see this Gunn-Peterson trough. And as a bonus to that, you also get the metals that are in absorption along the line of sight. And so that's how we use metals to probe reionization. And I'm going to be talking about a particular survey, a large program on the VLT called XQR30, and I'll introduce that in a moment. But in a nutshell, what we see is the products left over from the first and second generation of stars. They're ejected out into the circumgalactic medium. Most likely are the things that we're observing, and we observe those along the line of sight. I'll give TNG another 1.5 seconds of coverage here to explain the fact that the difference between looking for hydrogen reionization that's in Lyman alpha, which is distributed everywhere, is of course the metals come from inside of the galaxies, and then they need to get out to the CGM, and the time taken to get metals all the way out to the intergalactic medium is a pretty hard task at these very high redshifts where you've just got a very short amount of time. So we need to take that into consideration when we're interpreting things. Okay, so Steve showed this diagram already. It's from 10 years ago from McDowell and Dickinson's, showing the star formation rate density. And we know from all the fabulous work that has been going on with JWST that this, it continues to decline, maybe not as quickly as we originally thought, but the status quo, 10 years ago, is that if we take this black line here and you do an integrated fit and you assume an adopted stellar yield and a return fraction of metals, you can reproduce what is known as the evolution of mean metallicity in the universe. Okay, so galaxies are biased traces of metals, and they sit above the mean metallicity line. So SDSS galaxies, you look at iron and galaxy clusters, that all sits above the mean. Things like damp Lyman alpha systems, oxygen-6 in the Lyman alpha forest, and all the way out here looking at carbon-2 and carbon-4 absorption lines in the circumgalactic medium at very high redshifts, had quite a large error box on it. And this was work that was started 15 or so years ago when I was a postdoc here at the IOA, working with Max Bettini and Pierre Medal, looking at these very first SDSS discovered quasars at a redshift of 6 and looking along the line of sight using first light instruments on the VLT. And it was based on very few lines of sight for those very first quasars. And so there were a number of us working in the field at the time who decided that it was time to do a large program using X-Shooter on the VLT. So we got together, we've got now 42 quasar spectra. They've got excellent signal to noise, a resolution of 10,000, where you can really go after all of these metal lines and get a really quite good sample of these metal absorption lines. Of course, there's many other wonderful things that you can do with the data. So there's other members of the large program who've looked at the black hole masses and, of course, looking at reionization from the Lyman alpha point of view. But my group has been focusing on the metal lines. So this is just showing you that the XQR30 sample gives you, many more lines of sight, better resolution and so forth. This is an example of one of our oxygen 1 absorption line systems that is detected in a whole bunch of other elements. Okay, so this is the catalogue that was put together by postdoc Rebecca Davies. My point here is that no galaxies were harmed or even viewed in the making of this catalogue. So we are just sending random lines of sight through the universe up to a redshift of 6 and seeing where the metals are. Okay, some of these things are quite complex, other things are just single lines. And we've got this fabulous catalogue of absorption line systems that probe different ionization energies that we can then use to describe the universe. The first thing that we looked at is the cosmic mass density of carbon-4, and we see that it declines quite smoothly in elements of 100 million years over this cosmic time from 4.7 down to 5.8. So, oh, I'm missing a slide. Anyway, there was another slide in there that showed that we looked at this to test the question of whether it was metallicity or whether it was the UVB, and we found by looking at the rate of change of omega carbon-4 that it's probably a combination of both, and metallicity alone couldn't explain that. Thank you. The real litmus test then comes in what's going on with carbon-2. So triply ionized carbon goes down, singly ionized carbon, carbon-2, goes up. So in this very short amount of cosmic time, the only possible explanation for that is that the UVB is rapidly changing. Not just along a couple of lines of sight, but in on average on all lines of sight that we've looked at. And we've got 42 of these. Oxygen 1 goes up. Weak magnesium 2, which traces both the higher ionization gas and the lower ionization gas, continues to be flat over this cosmic period of time where metallicity should be going down. So this is evidence for a weaker or softer UVB occurring in the circumgalactic medium. Okay, so I will give you my summary again. So this is evidence of a late reionization continuing to occur in metal-enriched and therefore biased regions of the universe. The outstanding questions is, did the CGM remain self-shielded while the local IGM underwent reionization? And does a self-shielded CGM then contribute perhaps to an efficient star formation? So the things that Steve was talking about earlier in this session and the things that we're seeing with JWST. And I'll leave it at that. Thank you.